Red. I think that, ooh, I could be wrong, but I feel like this is the end of the road as far as this unit is concerned. So this will be the last thing we learn, and then we'll practice this for a couple days. Um, and then it'll be time to get into, I'll probably give you a quiz first, and then there'll be a district assessment on the heels of that. I will tell you that what I know from the past is that the district assessment in Unit 1 for Algebra 2 is pretty easy. So that's some good news. And district assessments, I just always make them worth 100 points. So if you get, if it's only like 42 points and you get 40, I'll divide 40 by 42. And then that percentage is what I'll put in out of 100. So it's a good opportunity if anyone has a grade that they don't like. Next week or two coming up, week and a half, great opportunities coming up to get the grade to go up. So something to think about. Anyhow, the reason this is its own lesson is because I'm not going to give you anything. I am, of course, going to teach you the rational root theorem, but what's happened in the past is I've given you a function like this and said, find the zeros, and I give you a freebie, right? That's what we've been doing for a couple of days. And in the absence of a freebie, our only hope here would be to look at it and think, well, maybe I can use grouping. And then you realize that's not going to work. You see it right away that if you tried to group this, you could get x squared out of the front, leaving x plus 5, and then you can't get anything out of the back. So grouping's out. And this is where it's kind of, I view this kind of like the quadratic formula. It's not as ubiquitous. Like the quadratic formula is just, it's like everywhere. We can use it so many times. The rational root theorem is a little more of a niche thing, and it's not always useful. But I can tell you that in all the problems we do today and on the homework we're going to do today, that there will be at least one rational zero, and you'll see why that's important. Because if all the answers were like weird, irrational or imaginary things with eyes, then we'd have some trouble. But there is always going to be at least one to be found, which begs the question, then how do I even get started? Because if I gave you a freebie, then we would synthetically divide it in and we'd get our little quadratic remnants and then we'd solve it down from there. In the absence of that, we need another tool, and that's what the rational root theorem is. It's going to look a little weird at first, but honestly, what it comes down to is just simple fraction building. What the rational root theorem states is this. Here it goes. Like, I want to know how to find the zeros, and I can't right now, but the rational root theorem says if you take the number in the back and the number in the front, what number is in the front of this? Correct. So if you take those two numbers and you build all possible rational values or fractions out of them, if there's a rational root, it will come from that list. And that should make absolutely no sense. But let me show you what this looks like. So you always take the one in the back, in this case 15, and you make a list of all of its factors, and they go on the top of a fraction. So I'll use green for this. I'll try to stick with the color theme here. So what I'm going to do is I'm going to take the number 15, and I'm going to make a list of all of his factors. And they are 1, 3, 5, and 15. Now, on the bottom of a fraction, right underneath those, I'm going to make a list of all the factors of the number in front. I thought I'd start us out with a couple where this is pretty stress-free. The number in front is 1, and what are the factors of 1? Just 1. So this will, I think, take more life, more form, more shape in the third example today. But for these first couple, I wanted to warm us up just with the concept of this, to the idea of the rational root theorem. Now, here's what it says. You have to take every possible combination of the numbers on the top and the numbers on the bottom and make fractions out of them. And if there's a rational zero to be found, it's going to come from that list. And by the way, when we use the term rational root theorem, understand that you're going to start to see two words interchanged like all the time. And a rational root theorem could also be called the rational zero theorem. So when we talk about, if you hear me slipping back and forth between using the word root and zero, I'm saying the same thing, that it's just different verbiage, different words. Okay. So according to the rational root theorem, if I'm going to find a rational zero, it's going to come from a fraction that's currently on the board. The question is, what are the fractions? Well, if I pair these two together and use them as a pair, what number do you get? What's 1 divided by 1? And by the way, all positive and negative values are what we call candidates. So when we make a list, which is what you're going to have to do on every problem, we always do positive, negative, like this. Now, let's do another pair. If I pair these together, and I'm not going to draw these little boxes every time, but if I made a fraction out of those, what would I get? 3 over 1, which is 3. So another possible rational root is either positive 3 or negative 3. And we continue. Another possible rational zero comes from the yellow box, 5 over 1. You see why it's beneficial to have 1 on the bottom, because anything over 1 is just the anything. So that's why I say we're going to warm up nice and slow with these. And so our second possible set of candidates is positive and negative 5. And then the final possible pairing comes from these two numbers here. The 15 and the 1 make 15. How many numbers do you see in that list? There are 8. Correct. So that means that we're now going to go on a guessing game adventure together. This is where it helps to be really good and quick with your synthetic division, because we're going to guess different numbers, and we're, for the first time ever, going to find failures in our synthetic division. I've made sure to this point that every time you do synthetic division, the last number you get should be a 0. That's going to change today. We're going to get numbers at the end that mean that there's a remainder, which means that we didn't find a 0. So far, so good. So now we embark on the guessing. So what we're going to do is we're going to take the numbers off of our polynomial, which, remember, go back to the very beginning. The numbers up here in this are what we're going to use now for synthetic division. So the numbers are going to be 1, 5, negative 29, and 15. And, you can't do what I'm about to say on a quiz, but we can do it when we're just doing like daily assignments. Divide and conquer, right? And that is like if Kane and Kaysen and Hugo are working together, they could say, hey, I'll try the 1s. Hugo, you try the 3s. In Kaysen, you try the 5s or something, right? So we can divvy the task when we're working sort of collaboratively, which is nice. But this is where we just throw caution to the wind and we guess. So what would you like to try first? 1. I mean, I'm a structured kind of guy, and so if you ask me, which you didn't, but I would start at 1 and I just work my way through the list from left to right, because that way there I can stay organized and I never have to wonder what I have and haven't checked before. So there are 8 candidates on the list, and we're just going to try the number 1, and we're going to see if it works or fails. And you'll see finally what it looks like when the rational or when the synthetic division doesn't work. Again, that hasn't been something that we've been exposed to yet. But if you drop the 1, be prepared to do some erasing today. I wouldn't write too heavy just because of the amount of erasing that you're going to have to do. So normally, we've been able to commit to the process knowing that the 0 is a foregone conclusion. Today, expect a lot of erasers. So again, light writing is probably a good idea. So drop the 1. 1 times 1 is 1. 5 plus 1 is 6. 1 times 6 is 6. Negative 29 plus 6 is negative 23. And you could stop. You can stop at any point when intellectually you make the observation that it ain't going to work. And I think you would agree that we could stop. If you're pretty good with numbers, you could have probably stopped a little bit before this. But if I were to continue, and I'll just show you what happens. If I did 1 times negative 23 and put negative 23, 15 and negative 23 make negative 8. And you can see then that failed. Therefore, 1 is off our list, right? So we grab our erasers and we erase. Let's try -1. And so, but again, these numbers all still have to be erased. We have to clear the workspace. And so we go back to the drawing board and we say, like Kane said, well, let's try -1. Okay, so 1 down, 7 to go. I mean, that's a lie. 1 down, maybe worst case scenario, 7 to go. But maybe we'll find it right now. Maybe we'll find it 2 minutes from now. Who knows? But if we try -1 now, let's see if we get a hit. And so if we drop the 1, 1 times -1 is -1. Add those, you get 4. You get -4. And I think you would agree again at this point, just based on the vibe, the flow, that we could probably stop. Do you see how it ain't going to work? Okay. So at this point, we can take 1 and we can also take -1 off of our list. And we're on to the next batch. Who would we try next? Probably 3. We're not, again, if you by chance misunderstood anything I said, we're not going 1, 2, 3, 4, 5. We're only testing candidates off of the list up here on the white box. Like those are what we call candidates. Those are the potential rational zeros. We don't know. So let's try 3. Drop the 1, 3, add 8, multiply 24. Can you kind of feel it happening right now? What's -29 plus 24? Mm-hmm. And we got a hit, because 3 times -5 is -15. And that gives us our 0. What this means for us is that we have done what we needed to do. We went in and, using the rational root theorem, we tested candidates until we got a hit, and we found a hit, which means at this point, I can commit and say that one of my answers will be x equals 3. And I would venture to say this, that if you don't know how to find the other two, I failed you, and I'll try to do better. What do these 3 numbers down here represent? It's a quadratic. And we should at this point understand that there is not a quadratic on the face of this planet that we can't solve, right? We're powerful like that now. We get it. We have the quadratic formula in our back pocket. So at first I would give it a glance and see if maybe it could be factored. It's going to be, I think, very obvious very quickly that that's not factorable, right? So we go to our backup plan, which is the quadratic formula. So A is 1, B is 8, C is -5. You're going to find that this assignment isn't all that different once you pluck out what you need. Like, and I'm not going to give you any yet today that have multiple. Yeah, that's kind of a lie. Eventually, we're going to go to 4th degree polynomials where there's 2 that you need to find using the rational root theorem. But for now, we're just going to get the 1 using the rational root theorem, and then the others will be predictably quadratic. And we pluck them out that way. So what would our quadratic formula say with these 3 red values? X equals what? -8 plus or minus of 64 Mm-hmm. And then I'm going to go backfill. And I've said this to you before, but the reason I do it this way is because I feel like sometimes if we're in the problem and just going boom, 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 the human brain sometimes confuses, and people sometimes put the wrong numbers in the spaces. So that's just why I do it this way. If it drives you nuts, I'm sorry, but it's what I do. So now I'm going to reset my brain and go back, and I'm going to put A where he belongs, and I'm going to put C where he belongs. And what's going to be inside of our square root?
64 plus 20.
64 plus 20. Very good. Changes to plus because the minus and the negative, they eventually get together. And 64 plus 20 is 84. So at this point, we're looking at x equals -8 plus or minus the square root of 84 multiplied by 2. How do you feel about the square root of 84? It doesn't square root for sure. Like it's not a square rootable number, but there is some meat on the bone. You guys know the way to break down 84? That's the only one we're looking for there. So if we take 84 and we break it up into 2 square root signs like this, we put a 4 in the first one and a 21 in the second one, we wind up with 2 square roots of 21. Okay. So we're going to replace the square root of 84 with this. So this is going to go and take over for this guy. Tap him on the shoulder and say, you're out, I got this. And so now we have x equals -8 plus or minus 2 roots of 21. And the Dorito in this case does come into play. All the even numbers in the triangle would tell us that we can reduce them all by 2. So if we do that, what do we get?
Plus or minus 20, the square root of 21.
Perfect. And we leave it like that. The ones that we get here and here are the ones that we don't need, right? Remember, ones only stay if they're in the placeholder spot before the plus or minus sign. So we get x equals -4 plus or minus root 21, comma, x equals the one that we discovered on our own, x equals 3. So we went into this problem expecting, bless you, we went in expecting 3 zeros from the beginning. We knew this because, wow, that's a lot of writing because of up here, right? So we knew to expect 3, and we walk away and say, I found 3. They are 1, 2, 3. Got it? Okay, let's do another one. So your next function is f of x. And again, one more kind of warm-up-y one. So we have x to the third. It's going to look a lot like the first one, plus 5x squared minus 31, x plus 21. And again, what you're used to seeing after this is like, ooh, f of blah, blah, blah equals 0. At this point, it's a mystery. So the step one, and you don't have to like this, but this will be an expectation. So I'm going to make sure you're listening when I say this. You have to make a list of all possible. That will always be in the instructions. Be clear? That doesn't mean in your head. It means like on paper, you have to write out a list of all possible candidates. And again, we're lucky here because the number in front is a 1. And so remember, it's always the numbers in the back, the factors of the back divided by the factors of the front. And when the front is a 1, we're like, I don't need fractions this time, right? You get that. So I'm just going to get right to it and make a list of candidates. What are the factors of 21? Perfect. So our candidates are either positive or -1, positive or -3, positive or -7, and positive or -21. That is what I have to make, is that list of candidates. Okay. So we begin. So it's time to take the numbers off the polynomial and get them all prepped and set up. So we have 1 for the x cubed, 5 for the x squared, -31 for the x, and 21 for the constant. Set up your division sign, and we go. I know that sometimes when I do this, especially when I used to do it with super hard problems, I would write this part in pen just because then when I went on, like sometimes it takes like, I'm sorry, but like 12 or 15 tries to find a hit. And then if it's pen, then I don't have to worry about erasing it, but that's just me. So again, I'm going to start structured with a 1, and I'm going to go through the algorithm 1, 1, 6, 6. And again, I'm going to stop here because I know that it's going to be -25, and I know I'm not going to hit it with a 0. So I can take 1 off my list, and then I move robotically to -1. Give it a shot. Drop the 1, -1, 4, -4, and again, I stop. You can see that it's not going to work, right? Okay, so we're done with the ones, and we erase, and we try 3. Drop the 1, 3, 8, 24. This one's looking pretty good. All right, so -31 plus 24 is -7. 3 times -7 is -21. We got a hit. Okay. And then we're left with a quadratic yet again, another quadratic that is not factorable. And so the quadratic are x squared plus 8x minus 7. If under different circumstances, like if that was a plus at the end for the 7, then I could do x plus 1, x plus 7, but it's not. It doesn't work. And so I've got to go the quadratic formula route again. So a is 1, b is 8, c is -7, and we're off. So quadratic formula is going to say that x equals -8 plus or minus the square root of, yeah, like I said, a lot of similarities between these two problems, right? -4 blank blank, all divided by what? 2. Go backfill A and C, so make sure you put them in the right ones in there, 1 and -7. And this time it's going to be what inside the discriminant?
64 plus.
64 plus 28, which is 92. So we're faced with always like the crossroads that we get to, the kind of place where we take pause and we assess and say, can I do anything with you? So that root's going to fall into one of three categories. It's either dead, square rootable, or simplifiable. What do you think about 92? 4 times 23. Very good. So and again, if you take 92 and break it down, you should always break it using two empty square root signs like this. And then you use 4 and 23. Remember that the answer is not 4 root 23, right? It's root 4 root 23, which is 2 root 23. And then we sub that in, and we're going to see the Dorito again. So we're going to have now, we're working with -8 plus or minus 2 roots of 23 divided by 2, Dorito it down, and you get a very similar answer. So these were cut from very similar chunks of cloth, these two problems. So our answers are x equals -4 plus or minus the root of 23, and again, x equals 3. So far, so good. All right, let's head on. On to the next. So these are a little tougher. So we're going to get f of x equals 2 x to the third minus 3 x squared plus 8 x minus 12. No freebie. So we're going to make a list of all possible rational zeros, and we're going to do it. This time I'm going to go back to showing my work. Because the number in front is a 2, that means that fractions are now in play. So the number in back is -12. You do not need to consider it as a negative for the rational root theorem because of the positive negative. So just view it as the number 12. And we're going to make a list of all possible factors of 12. What are they? 1, 2, 3, 4, 6, and 12. The number in front is a 2. And the factors of 2 are 1 and 2. Fractions are now in play. So what I like to do is go through and acknowledge all the whole number candidates first. And so when I make my list of possible rational zeros, I'm going to start my list by saying positive, negative, all of those. So positive, -1, positive, -2, positive, -3, positive, -4, positive, -6, positive, -12. So we already have 12 candidates on the board. But now there's going to be more because now we have to consider every possible combination of the numbers on top paired with the second number on the bottom. So I'm going to draw some little shapy things and I'm going to kind of undo them as I go. If I made a fraction out of those two, what would I get? Which I already have, so I can ignore that. Okay, no repeats. If I make a fraction out of these two, what do I get? Good. So now I need to add on to my list a new candidate, which is positive, -1/2. Okay, so I'm going to be pretty structured as I go through this. I'm just kind of methodical. I work my way from left to right. I'm no longer going to consider the over ones. So, because we've already been down that road, I don't even know why I brought it up last time. But let's talk about 2 over 2. What does that give us? Which we already have. So we can discount 2 over 2. Let's head to the next one, which is 3 over 2. What does that give us? 3 halves. So we now need to add positive negative 3 halves to our list of candidates. And our list is now up to 16 items instead of 12. The next one is 4. What do I get if I do 4 over 2? Already on the list, so we can discount that. Okay, we're going to head across to the next rational 0, which is 6 over 2. What does that give us? Which we already have. And then the last one is 12 over 2, which we already have. You will find a lot of times when there's a lot of even or a lot of odds, mostly with evens, that you're going to find a lot of redundancy and you can just skip them. But you go through, you acknowledge all possibilities, often only to find that they've already been covered. So we have 16 things. If we're the world's unluckiest person, then we would take 16 tries. So let's see how this goes. Anyone have any thoughts on what you want to try first? Well, first, let's set up the numbers, I suppose. So we're going to do 2, negative 3, 8, and negative 12. Set up your upside down. I'm going to scroll this up a little bit. We don't need the original problem anymore. Where do you want to begin? This is tough because you're looking at a potential for 3 or 4 or 5 minutes of failures. Where do you want to start? Just want to start with 1? Okay. Since only one person had an opinion, I'll take that opinion. So I'm going to go through and work the 1. 1, 2, 2, negative 1, negative 1s. It's a fail, right? You can see it's a fail. 7s aren't going to make 12s. So 1 is off the list. What else do you want to try? Negative 1? It's at this point where you could really see the benefit, like with Katie and Emma working together, or you boys, or you girls, or whoever, you two back there working together helps a lot because, again, this is where it really helps for Kane to maybe say, hey, I'm going to take the back side of the list, you take the front side, and we'll work towards each other, or something like that. Anyone try? You tried it? It worked? Okay. So it helps sometimes to not be so structured, like I said. In a case like this, like Mari just decided, let's go to the back of the list and see if my teacher's maybe hiding a fraction from me. And so Mari said, you know what, let's skip ahead. Let's maybe not a bad idea. Let's try the fractions first, thinking that maybe that's what someone wants me to find. So if we skip a whole bunch, skip, and get all the way to the end and test one of our possible rationals, 3, 0, or 3 halves, let's see what happens. So do the math, drop it down, 2. What's 3 halves times 2? Okay, good. 3. Add those together, you get 0. What's 3 halves of 0? 0. Add those together, you get 8. And what's 3 halves of 8? It is 12. And there it is. So teamwork makes the dream work in a case like this. I mean, you could have spent 3 or 4 minutes. I mean, unless you suck at synthetic division, then I'm sorry, but it would take you 10 to go through that whole list. But the quicker you are with your basics, no little mistakes. But that could have taken a long time. But thankfully, someone started from the back of the list and helped us out. So we found our rational 0. And so we can now say that x equals 3 halves is a 0. Get that one off our to-do list, and we're down to a quadratic. And the quadratic now isn't about, we don't need the rational root theorem ever once we get down to quadratic fill. Because it's a quadratic, right? So these numbers represent x squared, x, and constant. And if I divide them down by 2, I get 1x squared plus 4 equals 0. Right? The 0 means that there is no x term. And this is one of those cute little quadratics that we learned how to solve a few days ago that's missing its middle term. So what's our attack strategy? Should be quick. Move the 4, which gives us right away, we know we're going to have i's in our answer because we're going to get a negative 4. And you can't take a real square root of a negative number. But we can still square root. That's fine. You can always square root. You just might get i's. No big deal. So we're going to get x equals positive or negative. And what's the square root of negative 4? 2i. Well played. So our list of answers is x equals positive negative 2i, and thanks to Mari, x equals 3/2. Okay. Without the rational root theorem, we never would have known where to even start. We never would have even known. If I haven't made this clear, the rational root theorem is a tool. It's a tool now that you can carry with you to help you find zeros. That's all it is. It's a little helpful tool. It's like your little calculator. Last one, and then I'm going to have you get to work. Okay, I think you probably understand this, but let's do one more. Our function is f of x equals 4x to the third. And again, these are all today going to be cubics. So rational root theorem, you hunt, find one, quadratic, solve it. So that'll change, just not today. So plus 3x squared minus 12x and minus 9. So we start by making a list of all possible candidates. The number in the back is a 9. What are the factors of 9? 1, 3, and 9. And then in the front, we have a 4. What are the factors of 4? 1, 2, and 4. So if there's 3 on the top and 3 on the bottom, that makes 9 possible numbers. However, again, you're going to find some repetition, right? So you'll see a couple things along the way. You're like, I've already done that. So rather than 9, we can expect maybe 6 or 7 unique ones, something like that. So first we start with just using the 1 on the bottom. If you think of the 1 as a part of every fraction, then you can just right away get your easy part of your list done, which is positive negative 1 over 1, positive negative 3 over 1, positive negative 9 over 1. Done. Okay. Now if we switch over to all possible ones that have 2 on the bottom, what's the first one? Positive negative 1/2, second one. Positive negative 3/2, third one. Good. And so we haven't seen actually any repetition with this. And the reason, can you see why there's no repetition? I lied to you. Why is there no redundancy here? What? Right. The top numbers are all odds and the bottom numbers we're working with evens. And so odds and evens are like, hey, we're not going to really, that's not true across the board, but that's what's happening in this case is that odds and evens, they're not compatible, right? So now we're going to go on to the ones that use 4 as their bottoms. And what are those? Positive negative 1/4, positive negative 3/4, and positive negative. Good. Again, we just have, at this point, have to divide and conquer and team up, strategize. If we all start with the same ones, we're all going to be equally inefficient. So I'll leave it to you guys for a minute or so. I'm going to get my numbers copied down. So I have my 4, my 3, my negative 12. This is your workspace that you're setting up. It's like your desktop. Get it set up, make it nice, and we begin. So if we work as a team, all of you at different places, it shouldn't take us, in a class of 15 students, it shouldn't take us all that long to find a hit. Pause the video because I honestly don't know if this will take 10 more seconds or 5 more minutes. So I'm going to pause real quick and I'll unpause once we find one. So you said what, 3/4? Okay, let's try negative 3/4. So if we stick negative 3/4 out here and we go through the algorithm now, which fingers crossed, and you can see how much it breaks my heart when a kid has the right one picked and then they make a dumb little 6th grade math error, like a negative times a positive, and they put a positive, or they say something stupid like 4 times 2 is 6. So you really have to hold yourself accountable. We're all human, but we can still strive for perfection, right? So when we're doing basic skills math like this, you want to be perfect, because what a shame if you have it in your grasps and you let it slip through, then you go and waste 10 more minutes like I had it and I never even knew it, right? So be spot on with this. What's negative 3/4 times 4? Negative 3, add those together, get 0. What's negative 3/4 of 0? 0, negative 12 plus 0 is negative 12. And what's negative 3/4 of negative 12? Positive 9 all day long. Thank you, Irene, for finding that for us. So we did it. And again, if you're a left to right person, that could take a while, right? It's hard. And I wish there was some magic I could give you, but there's really not. The rational root theorem is the only magic I can give you. You know, where you start and the direction you go, that's up to you. So that could have taken a long minute, but we did it. Irene did it. So I'm going to take all the numbers now, the remnant numbers down here. Might as well divide them all by 4. And that's going to leave me with 1x squared minus 3 equals 0. And we're so powerful now, like we're not scared of little quadratics like this. We're going to add 3, take the square root of both sides, and we're going to get x equals positive or negative root 3. And that's that. So as far as making a formal list of the zeros, I would say x equals positive negative 3, comma, x equals negative 3/4. And that, guys and gals, is how you use the rational root theorem. So where this gets buffed is when I give you like a 4th degree polynomial that has 2 rational zeros. And you find one and you're feeling like I'm pretty awesome. And then you're like, well, crap, that's only half the battle. Because then you have to go and use the rational root theorem again and find another one. I mean, you don't have to restart the rational root theorem, but you wind up sometimes having to cherry pick, boom, and then another number off the list before you can get down to quadratic fill, but not today. So any questions? All right, your assignment is on Canvas. It's just a PDF. There's, I think, 10 problems. It's not a lot. Your instructions are to make a list of all possibles and then find them all. List them all, find them all.